So in today's lesson, we're going to be talking about acids and bases. And so I'm not sure how much you remember about acids and bases from grades 9 and 10 in the chemistry sections. And so what I've done is I've constructed this table here. And what I want you to do is tonight, before you move on to watch the rest of the video, is I want you to do a little bit of research on some of the differences between acids and bases. What you may remember right now is that acids and bases are chemical opposites, and of course they combine and neutralize one another. And so here's some highlights that I'd like you to make sure you understand before we move on. What if we were to taste them, what would they taste like, what they feel like, how do each of them react with metals, if at all? What about electrical conductivity in solution? And what about reaction with a litmus paper? So those are some items that I want you to make sure that you take a look at. And so along with that table that I'm asking you to fill out, I just want you to peruse or take a look at this list of some common acids. And usually when I'm teaching a lesson like this, people will come up with some familiar acids. Generally, people have an easy time remembering what some of their household items are that qualify as an acid are, right? So lemon juice often comes up, and vinegar and things like that. So what I also want you to do is take a look and see what the chemical name for the acid that is in that common household substance is. So bases, common bases, here are a list of them, and what it is within that particular substance that is making it basic. So for example, soap. Most of the soaps that we have in our home are potassium hydroxide, or they might be something called sodium lauryl sulfate, but they will act as a base. So as I've said, finish this bit of work before you move on, just so that you're familiar with some of the ideas related to acids and bases. So most of what we've just talked about is sort of superficial stuff, right? But this is the grade 11 chemistry course, and so of course we're going to get into a little bit more detail than that. So in chemistry, there are different ways of defining acids and bases, and the way that you probably remember from grade 9 or grade 10 is what you will now understand to be what's called the Arrhenius definition. So the Arrhenius definition basically describes an acid as something that produces hydronium ions in solution. So for example, let me break this down a little bit for you. So last year you would have said, well, if I have HCl, which is an ionic compound, and I dissolve that in water, it's going to ionize, and that will form an H plus or hydrogen ion and a chloride ion. And the water's still kind of there, and these ions are just dissolved in it. Now, a more mature way of looking at this from a chemistry perspective is to look at, well, what happens with this H plus in relation to the water? Well, it turns out that hydrogen ion is more stable, being a part of the water molecule, and the two of them join together to form what we call a hydronium ion, right? So let's just look at the charges here. So a water molecule, there's no charge written over here, so it's neutral, with a 0 charge overall. And this plus hydrogen ion has a +1 charge, so it has a +1. So if I take a particle that has a +1 charge and add it to a particle that has a neutral charge, then the overall charge on the new particle will be +1. Okay, so hydronium ion, all that is the ion that forms when a hydrogen ion joins with water, forming something with the chemical formula H3O+. So just to recap that, H plus, my hydrogen ion, is not going to exist in water, but it's going to join with our water molecule, forming our hydronium ion. So by definition, an Arrhenius base is something, a substance, when placed in water, produces hydroxide ions, right? So the hydroxide ion is a chemical opposite of the hydrogen ion. And so a good example, a common example that we use is if we were to take sodium hydroxide and make an aqueous solution of it, then what we would have is we'd have our positive sodium cation here, and we'd also have our hydroxide ion. And so that makes sodium hydroxide a base because it's releasing these hydroxide ions. So I've got a video here that I'm going to post the link. I'm going to post the link to this YouTube video on Google Classroom for you to watch as well. But maybe save that to the end just as a consolidation piece once you've watched this video. And so the next thing I want to talk about is a different definition, a definition for acids and bases that you will not be familiar with, but that is very commonplace in the world of science. So you'll notice here that in the case of the Bronsted-Lowry base, so I'm going to come down here and talk about Bronsted-Lowry bases, right? So you'll remember that our Arrhenius definition talked about a substance that would release hydroxide ions in solution, right? And so let me just take a minute and go back to our note on Arrhenius. So if I look at the formula for an Arrhenius base, NaOH, I can tell very easily that that contains the hydroxide ion, and that is a really good indicator that this substance will release hydroxide ions in solution and form a basic solution. And so what some scientists discovered was that there were substances like the ammonia molecule that I'm showing right here that would in fact in solution produce a solution that had a pH that was above 7. It was an alkaline solution. So how the heck is it that something that doesn't appear to have any hydroxide in it form a basic solution? And that's where they sort of retooled their definition of what constituted an acid and a base, or the mechanism of how they're produced. They needed to kind of fine-tune that a bit. And that's where we come up with the Bronsted-Lowry acid-base definition. So a Bronsted-Lowry acid is what we call a proton donor. So in chemistry, a proton the term proton is often interchanged with the hydrogen ion, and I can explain that to you by drawing a quick picture of the hydrogen atom. So you'll remember from the periodic table that a hydrogen atom has a mass number of 1.01. Sorry, that's an atomic mass of 1.01, so a mass number of 1. And also an atomic number of 1. And so when I look at that, the difference between them tells me that there are 0 neutrons when I do this subtraction. So a hydrogen atom will have simply its proton in the nucleus, that 1 proton, and it'll have 1 electron in its orbit. There, right? But if I'm talking, so this is just my plain old hydrogen. But if I go ahead and I want to form an H plus ion, that means I need to remove an electron from my hydrogen atom. Right? So in other words, get rid of that. And when I get rid of that, all that I'm left with, I have no more electrons. All I have is just that lone proton in the nucleus. So that's why we can use the term proton to represent a hydrogen ion. Because in essence, a hydrogen ion is just an atom with no electrons. So let's get back to the Bronsted-Lowry acid definition. So it would Bronsted-Lowry acid is something that donates a proton. So I'm going to look at my acid. Okay, this is water. I'm going to look at my acid and locate the proton. Here it is. And it's going to act as a proton donor. That means a proton giver-awayer. And so it's going to donate its proton to water. And when it donates its proton to water, that's going to give me, surprise, surprise, my hydronium ion. Bear with me, people. There we go, right? But I need to take care of the leftovers here, and that's this acetate ion, right? So if H plus is combining with an acetate ion, then the charge on the acetate is simply -1. So C2H3O2. Now, so there, that is a Bronsted-Lowry acid, proton donor. A Bronsted-Lowry base is a proton acceptor. So in this case, here's ammonia that I'm using as my base. So it's going to accept a proton. Where is it going to accept it from? It's going to accept it from the other substance it's reacting with, in this case, water. So when water loses a proton, it no longer has two hydrogen ions, it only has one, and that's actually where the hydroxide ion comes from. So even though the hydroxide ion is not built into the chemical formula for ammonia, it still ends up being released in water when water donates a proton to ammonia. Right? So what does that leave as a result? Well, it means that ammonia is gaining a proton. So now instead of having only 3 hydrogen ions, it has 4. But remember that I'm adding a hydrogen ion to a neutral molecule when the hydrogen ion has a +1 charge. And so if I take something that's neutral and I add something that has a +1 charge, which is my hydrogen ion, then I'm going to have an overall positively charged ion. So you may have thought to yourself, well, in this case, if water is donating a proton to ammonia, since ammonia is accepting it, it's my base, right? But since water, it was the donor, doesn't that make water an acid in this case? Absolutely. Okay, so water in fact is an acid because it's a proton donor, according to our Bronsted-Lowry definition. Okay, if we were to look at the example that I used for Bronsted-Lowry acid, right, I know that this is my acid, right, and it donated a proton to water. So in this case, water was the acceptor. So water, in this case, was in fact acting as a base because it accepted a proton. So water, you'll notice, can be either acidic or basic depending on what is being dissolved in it. And it's all in reference to something else. So that brings me to my next topic, which is an acid-base conjugate pair. So sometimes a common question that will be asked in this section of chemistry when dealing with acids and bases is to identify the acid-base conjugate pair. And so what makes the acid and the base in a conjugate pair different from each other is a difference in a single proton or hydrogen ion. I think the best way to explain this is to kind of go through an example here. So I know that my ammonia and my ammonium are the acid-base conjugate pair. And I know that because the only difference between ammonia and ammonium is 1 proton. In a similar manner, I know that my nitric acid and my nitrate together form another acid-base conjugate pair, because what differentiates the nitric acid from the nitrate is the presence of this single hydrogen atom. So that's it. That's all there is to it. So as a secondary activity, here's what I want you to do. I want you to take a minute and I want you to identify for me whether each of these substances, each of the 4 substances, is acting as an acid or a base. Go. And when you're ready and you've answered the question to the best of your ability, I want you to continue with the video and check your answers. All right, so when I look at this question, once I've figured out what my acid-base conjugate pairs are, the easiest way for me to figure out which is the acid and which is the base is by looking at what happened to the proton from the start of the reaction to the end of the reaction, to after the reaction. And so I can tell from this reaction that in order to end up with these products, my nitric acid had to donate a proton to the ammonia atom, or molecule rather, right? And so in this case, that makes my nitric acid a proton donor. And by definition, proton donors are referred to as acids. Conversely, who is that nitric acid donating its proton to? It's donating it to ammonia. And ammonia that makes ammonia a base, being the proton acceptor. Now, if I were to look at this reaction in reverse, as though these were the reactants, then it would appear that ammonium is donating a proton to nitrate. And so if it's a proton donor, that makes it an acid. And my nitrate has to accept a proton because it doesn't have a proton to donate, and so that makes it a base. Now, another way to make sense of this is to say, well, I know that in a pair, one is an acid and one is a base. So if I know that this is a base, that means that my ammonium over here has to be the acid. Same holds true with this pair in blue. If my nitric acid is the acid, then that means the nitrate has to be the base. So if you weren't too sure about that, here's another example for you to try that we'll take up tomorrow. So I want you to identify the Bronsted-Lowry acid and base pair in this, and I also want you to identify label them as acids or bases. If you can do that for tomorrow's class, then we'll be ready to take it up. So earlier on in this lesson, I talked about how water can act as an acid or a base, depending on what it's reacting with. So, for instance, in this case, I can see that HCl, that's an acid, and so it's going to donate its proton. And so that makes water a base. In the second example, I can see that my ammonia has grabbed onto a proton. So in this case, my water is my proton donor, and that makes it an acid. So the name that we give to substances that can act as either acids or bases is amphiprotic. So let's make sense of that word. So amphi makes me think of amphibian. So amphibians are animals, organisms that can exist both on land and in water. Where the amphi prefix actually means dual. So there's a duality there. So amphi meaning dual, protic referring to the proton, that it's either accepting or donating. So it can do either the donating or the accepting of the proton. And so here's what I'd like you to do. I'd like you to write out a chemical reaction equation, two actually, you'll need to show how the H2PO4 minus ion is amphiprotic. Now I know that you can look this up online and find it, but what I'd like you to do instead is to try yourself, because ultimately on a test or a quiz, you're not going to have Google to rely on, right? So it's important that you understand how to work through this question. So you're going to need one question where, or one equation where it's acting as an acid, and a second equation, a separate equation, reaction equation, where it's acting as a base. And so that is what I'd like you to do as part of your homework for tonight. Be ready to take a look at this with us together as a class and to take it up. I'm also going to be posting some homework for you to try out in addition to that. And I'll post that homework on Google Classroom.